Okay, so this will be last class of the semester. And last week with Hiroki, he presented the agent-based modeling, which is very useful for modeling. Okay, again, we're having microphone issues. It's on.
It's on.
Yeah. Well, here it marks. Okay. So agent-based modeling is very useful for modeling complex systems. I mean, it's also has its disadvantages, but the fact that we can use natural language to describe agent-based models, uh, then it makes modeling easier for people without mathematical background. One might say that one disadvantage is that it's not so easy to do mathematical analysis with agent-based modelings as opposed to models, let's say, based on differential equations. So again, advantages and disadvantages, but then it's very useful to know them and to have them just like an extra tool in your kit. So today we're going to speak about limits of science and engineering. And of course, there are limits in science and limits in engineering, but in many cases, if we don't have a clear idea of what are these limits, then we might have assumptions that are misleading, if not completely wrong, or we can make the wrong assumptions or suppositions about things that are beyond our reach. So this caricature describes roughly what we do in science. We kind of get ideas and then we contrast it with experience. And usually our ideas are crap, and then we try to make better ideas until they withstand experience, and that's a constant cycle. Historically, we can say that science has been like our global search for truths, but you can never be completely sure of scientific truth because by definition, you always are open to falsify, even if we call it a law or a theory, and there's lots of proof in favor. Doesn't mean that it's applicable in all contexts. And classic example is Newton's laws. That is not that they are wrong, but they're not applicable at microscales or macroscales. So once our instruments and observations went beyond the scales for which that initial experiments were supporting that theory, it was not sufficient. Let's say it didn't apply to those broader micro contexts and macro contexts, but of course it's still valid for the context it was proposed. And I mean, this diagram more or less describes this. So we observe phenomena, whatever we want to understand. We make measurements with different devices, and we have mentioned that in many cases, the possibility of studying phenomena depends on which apparatuses we develop to make these measurements, like microscopes, telescopes, computers, and so on. So through this observation, we get data, and then we can analyze that data to build models. And in one of the first classes of the semester, we discussed a bit more deeply about roles of models in science. And we might generalize models into laws. And then the laws allows us to understand models. Models allows us to do many things with that data, to predict, to describe, to understand, and so on. And we check the consistency of data with phenomena. And this is a constant cycle. It's not like, okay, now we have the laws of the universe, or now we have the right models. And in engineering, we use data models and laws in order to control phenomena. And then depending on how successful that control is, then we can actually update our observation analysis, generalization, and so on. Because the best proof of a theory is when we can use it to control the phenomena we are describing. Actually, some people will say that the goal of science is to discover the laws of nature in order to predict the universe, to control it for our benefit. And say that has been the view probably since the times of Galileo, Newton, Descartes, Laplace, and so on. But of course, it's anthropocentric and it doesn't consider many of the limitations we will mention now, and assumes that we know best how to control phenomena. Not only, let's say, if we just look at the planet, let's say what would be the best for the biosphere, but for our own benefit. It assumes that we know what's best for us, and in many cases we have no idea. And yeah, we might want to maximize wealth, for example, of a company or a country. But then if we just take a strategy that would maximize whatever variable we're trying to optimize, that might deplete the source of that wealth, and then we end up without that source. And let's say it's that happens often with natural resources. It's I mean, from fairy tales, it's killing the gold egg-laying goose or something like that. Yeah. So a bit of history. In ancient Greece, due to so-called Pythagoras theorem, people knew, and I mean, even before in India and Persia, people know about Pythagoras theorem, only that they didn't call it that way. That if you have a square triangle which sides are of length 1, then the hypotenuse will be square root of 2. However, Greeks didn't have irrational numbers, and especially in the Pythagorean school, there was a strong striving for perfection, and it assumed that numbers were perfect, and it was like a reflection of the perfection of the universe. So something like an irrational number shouldn't exist, even when they also had a notion of pi, which is also irrational. But anyway, it was not a big problem because they were not working with numbers, but with ratios. So they could kind of avoid this question. And throughout the Middle Ages, it was put under the carpet. And it was until late 19th century that Georg Cantor, when he defined infinitesimals, I mean, we mentioned him. We discussed fractals because Cantor set is one example of an infinite set that contains itself an infinite number of times and so on. So when Cantor defined infinitesimals, then we could speak about square root of 2 and pi and so on, and irrational numbers, and then it was not a problem. So that was an example of a limit that was overcome. However, it introduced through after several decades other limits, much deeper limits in formal systems, not only mathematics. This includes logics and yeah, any kind of mathematics that we would like to develop. So Cantor defines set theory, which is now the basis of modern mathematics. But back in his time, he was accused of charlatan and corrupter of youth and worse, because of these paradoxes that you get when you study infinite sets. So, for example, the natural numbers, yeah, from 0, 1, 2, 3, and so on. It's an infinite set because there can always be a greater number. And then the set of all integers, which is like the positive and the negative numbers and 0, one might assume like, oh, it has twice the number of elements than the natural numbers because for every positive number, you have a negative number. Okay, let's assume that the 0, there's just one, but let's say we could have, in theory, twice the number of integers and twice the number of naturals. But then you can map all the negatives to a natural number, and you never run out of natural numbers because they're infinite. So for every integer, you can find a natural number that would represent it. So therefore, they have the same cardinality, which is the number of elements, which is infinite. So that kind of was problematic for some. And then real numbers, which include rationals and irrationals, you can show that you have more rational numbers than naturals in the interval 0, 1, because of course you have 1 over all the natural numbers, and then 2 over all, well, that's already not necessarily between 0 and 1, but let's say between 0 and 1, have 1 over all the natural numbers, 1 over 1, 1 over 2, 1 over 3, and so on. But so that gives you all the natural numbers. But then between each of those, again, you have an infinite number of numbers that you cannot put correspondence with 1-to-1 with the natural numbers. So therefore, the cardinality of the real numbers is greater than the cardinality of the naturals. So it's Aleph 0, it's the natural numbers. Aleph 1, it's the real numbers. And that was like problematic. So Russell with Whitehead worked for several years in their Principia Mathematica, which is same title as Newton's work, but basically we're basing all of known mathematics in terms of logic. And they tried to patch mathematics so to solve Cantor's paradoxes, but actually they couldn't. And somehow one of these paradoxes got the name Russell's paradox, which I mean, I won't get deep into it, but just to state it, set that does not contain itself as one of its elements, let's say the set of numbers 1, 2, 3, 4, let's call it set A, is respectable because it doesn't have itself as one of its elements. And the set B, which might have the elements 1, 0, the set A, and the set B itself, it's not respectable because it contains itself. And then the question whether the set of all respectable sets is respectable is Russell's paradox, because if it's respectable, then it doesn't contain itself. But then if it doesn't contain itself, it should contain itself, because if it's respectable, it contains the set of all respectable sets. So then it's not respectable. But then if it's not respectable, then it shouldn't contain, then it should contain itself. So then it's not respectable, and then it should be respectable. So anyway, paradox. And David Hilbert, who was one of the most respected and influential mathematicians of the 20th century, posed a program to prove that mathematics in particular and formal systems in general were complete, consistent, and decidable. This means that there shouldn't be any paradoxes within mathematics, like Cantor's or Russell's, that you should be able to say whether any statement is true or false. And so that would be decidability, consistent that there are no paradoxes, and complete that that you can prove any statement in them. And John von Neumann was doing one of his PhDs with Hilbert, and at one of the German Mathematical Society meetings, Kurt Gödel from Vienna presented his proof that only von Neumann understood, because he was working on this topic, where he basically showed that mathematics were not complete nor consistent. And a few years later, Alan Turing, also known as father of computing, defined his Turing machines precisely to prove that formal systems are not decidable as well. So if you read the title of Turing's 1936 paper, it's Uncomputable Numbers with an Application to the Einstein-Heisenberg's Problem, which is the decidable problem that Hilbert posed. So we could say that actually this limits of formal systems in an indirect way triggered the formulation of formal computer science. Because Turing machines were defined in order to show that the non-decidability of formal systems. And Greg Chaitin later also showed that no random number can be shown to be random, which is a related proof, not the limits. So, I mean, even when it's almost a century after Gödel, we are still not coming to terms to the implications of these limits. And Gödel himself in his later years, I mean, later von Neumann brought him to Princeton and many others. I mean, his classmates from Budapest, Einstein, and many other people. Von Neumann imported some just before the war. Gödel, he was ill, and then undecisive, and then his wife was also indecisive. So finally, Gödel agreed to come to Princeton already when the war had started, so he couldn't cross the Atlantic because of the U-boats. So he had to go through China and Japan, and then crossing the Pacific, and then by train crossing the whole of the United States. But anyway, he later became walking pals with Einstein, and he was in his later years still working, trying to find a roundabout to show that at least in some way formal systems would be complete or consistent. But of course, he had proven that that's not possible. But anyway, Henri Poincaré, who actually was one of the ones who was accusing Cantor of being a charlatan, French polymath, late 19th century, he won a prize launched by the King of Norway to solve the three-body problem. So Newton solved the two-body problem, the law of universal gravitation, and then more than 200 years later, 200, 300? Yeah, so Newton was 17th century, and this was 19th century. Yeah, more than 200 years later, it was like, well, why haven't people solved the three-body problem? It's just one more variable. I mean, so King of Norway launched a prize. Poincaré won that prize not because he solved the problem, but because he showed why it was so difficult to solve, and it's because of what we now call deterministic chaos, meaning that if you have three variables in this case, well, in general, there's this theorem that tells that for continuous systems, you need at least three variables to have chaos. In discrete systems, you just need one, like with a logistic map. But anyway, one can say that chaos limits predictability because of sensitivity to initial conditions. So this is something that people have worked, and there's this thing called chaos control, which kind of allows you to guide chaotic systems through a predictable trajectory. And also, we should remember that chaos is different from complexity. Sometimes we can have chaos, which is sensitivity to initial conditions, sometimes only complexity but not chaos, or we can have both or just one. And one of the implications of complexity is what people call non-reductionism, since interactions characterize complexity, then this might generate null information that is not in initial or boundary conditions. And this limits predictability because only once we get to the future, we will have that information. Technical term is computational irreducibility, meaning that there's no shortcut to the future. We need to go through all intermediate steps, like in cellular automata. I mean, this cellular automata rule 110, once you have run the system, since it's deterministic, you know, okay, from the same initial conditions, I will get the same final conditions. So in that way, you could have a shortcut, but it's not a real shortcut because you had to process all the intermediate steps. And I mean, you can compress a bit these transitions because you have these ether regularities, but not that much. In many cases, like for example, with Rule 30, it's quasi-chaotic system, so actually you cannot really compress much of that. And it's very simple system. I mean, you don't need to know even to add how to add. So it's like something that kindergarten kids can do. Let's say, in sense that very simple systems can lead to very high complexity. But a deeper problem about interactions is that these interactions can generate not only new information, which leads to computational reducibility, but it can also lead to new variables. So if we have already a state space that describes a system, even if we are not able to explore it fully, then we could do some analysis of it. But then if we don't know whether variables, meaning dimensions in this state space, will be added or removed, then let's say we don't really have the proper tools to describe these systems when the state spaces change like that. And in a similar way, another effect of interactions can be non-stationarity, which basically means that the phase spaces change at different scales. So for example, we can have a function, and then that function can change in time. So then we add another dimension to describe that temporal variation, but then the way in which that function changes in time can also change. So then we can add another dimension that describes how the change of the change changes, and so on. And let's say, again, this limits prediction, and we end up with situations where states never repeat themselves because the state spaces are changing constantly. So then our tools for doing prediction are limited. And of course, we can use adaptation to try to overcome these limits, but it's something that we have to consider. And
this is 1,000 monkeys working at 1,000 typeprinters. Soon, they'll have written the greatest novel known to man. It was the best of times. It was the worst of times, you stupid monkey.
So I mean, you might know this idea of monkeys on typewriters eventually writing the complete works of Shakespeare. And that's very easy to say, assuming, we have infinite time. And Turing machines also have infinite time, infinite memory. So we can make claims about computability in theory that in practice there will never be enough time in the universe to compute computable functions. And on the other hand, there are non-computable functions that in practice are computable, like if, let's say, the halting function of small Turing machines, we can, let's say, they're computationally irreducible and also in a way non-computable, but for some specific cases, we can just try it all. And it might be that we can find the result. And also, if we know enough about Turing machine, same Turing described that we can use an oracle to calculate this halting function. But then, of course, we will have a new Turing machine that includes the oracle, and then the halting function of that meta Turing machine would not be computable unless we get another oracle. So again, paradoxes. But then going back to the monkeys and the typewriters, I was just speaking about this with my eldest daughter, and just back of the envelope calculations, like, okay, how long would it take the fastest supercomputer to run through all possible combinations of 26 English characters and produce just the first page of Hamlet? So let's assume 500 characters. So the possible combination is 26 to the 500, which is a ridiculous number. I mean, number of particles in the universe is about 10 to the 80. And yeah, I forget how many seconds we've had in our universe, but it's 13 billion years, 13 point something billion years. So it's much less. Yeah. So anyway, I just made the calculation. Okay, if we had the fastest supercomputer we have now running from the Big Bang until now, those 13 billion years, exploring all possible combinations of characters, each, and assuming that each exploration would be just one flotating operation, which is more, but let's say just assume it's one flop. How many characters will you have? And you just calculate the logarithm, and it's 17 characters. So it will never produce some intelligible text. I mean, of course, evolution is not random, and that's why we have all the complexity we observe. It does not explore exhaustively all possible combinations. But then many of our tools assume that we have the capacity to explore exhaustively state spaces, and we can't. And in many cases where we have these huge state spaces, we can't even start exploring with statistical significance their state spaces. Because of course we can say, well, we don't need to explore them, we'll just do some sampling and we'll be fine. Some cases you can do it, most cases you can't. Yeah, so just a couple of examples. Most of all possible chemical reactions will never occur. There's just too many. So actually we don't know what could be the potential results of most possible chemical reactions. And also the current configuration of atoms will never be repeated. And actually, since there's so much uniqueness in our universe, actually come back to Wigner, who was high school classmate of von Neumann. He has this famous essays on the unreasonable effectiveness of mathematics. It's actually surprising that we can do science because there are regularities and we exploit those regularities to do prediction and so on. But and anyone knows why that picture is there? Yeah, it's from older generations. So okay, there's this classic film Blade Runner from Ridley Scott, and it's based on Philip K. Dick's novel Do Androids Dream of Electric Sheep? And this is this future where there are these replicants which are androids, so they're machines which look like humans, behave like humans, but they're not humans. So Harrison Ford has the job of actually identifying these replicants because they have become so sophisticated that in some cases you don't know whether they're humans or not. And actually, this phrase "more human than human," I think it's from here. And I forget the name of this character, but she's a replicant. Yeah. So, but then yeah, the replicants are these androids. That's how they call them. And it's a bit like a Turing test to see whether they're humans or not. And I forget precisely how they are able to distinguish, but more sophisticated replicants are getting very close to passing those tests. Actually, there are many sci-fi films where robots get sophisticated enough so that they can be as
So like maybe in the last 10 years or maybe when there are many this kind of movie.
Yeah, or even from the 1990s, there's this film called Nirvana by Giuseppe Salvatore with Christopher Lambert. And I mean, it's not a spoiler because that's like the first 10 minutes of the film. Christopher Lambert is a game designer, and his latest game, the main character is so sophisticated that he becomes conscious, or whatever that might be. But basically, let's say the game starts, and then somebody enters the room and says something, and then somebody comes him and shoots him and dies. But then he starts again, and then he starts getting deja vu, and then it's like the same person comes, and then he says, "Oh, now you will say this. Now this guy will come." But then he reacts differently. But he understands that he's trapped in a game, and he starts telling the other characters, "Hey guys, don't you realize we're not real? We're just in a game." And nobody says, "No, of course not. I'm real. I don't know what you're speaking about. You should be crazy." So this game character who became conscious decides that he cannot lead such an existence and somehow communicates with Christopher Lambert, the programmer, and asks him to delete him. And the whole film is like the process of getting into the mainframe of the big company that holds this game and erasing the character. But anyway, yes. Replicability, you might have heard about the crisis of replicability in sociology and psychology. So there have been these classic experiments made in the 60s, 70s, 80s, and they are used to teach undergrads all over the world. And I think it was around 10 years ago, or maybe a bit less, that there was an effort to replicate these experiments. Just like, okay, in science, we need to have reproducibility or replicability to test the theories. And I think like 80% of the experiments were not replicating the results that people that were originally found in the original studies. So people speak of a crisis because it's like, okay, we have been teaching these theories, but then the experiments which supported those theories have some methodological problems, meaning that they're not generalizable. The results are not generalizable because maybe it was just for a particular context that the conclusions were holding, and then if you change slightly, then turns out that a different explanation is better, or simply we have no idea of what is going on. But let's say continuing with sci-fi, we can speak about artificial intelligence. So Alan Turing, I mean, along with Claude Shannon and John von Neumann, who were some of the first people to work with computers, they wanted computers not just to be able to do lots of number crunching. They wanted to understand intelligence in Turing and Shannon's case, life in von Neumann's case. And of course, since intelligence and life are about information processing, you need computers in order to try to build some models about mind. So Turing did a very early chess program, which was very bad, but let's say it was more like a proof of concept. Shannon had a little rat robot that followed a maze. And von Neumann defined cellular automata, inspired by some experiments of Niels Barricelli, who worked with him in Princeton. There's this claim by Barricelli that von Neumann stole his idea and so on, but well, whatever. But anyway, going back to Turing, in 48, in a lecture, he mentioned that if a machine is expected to be infallible, it can also be intelligent, meaning that usually we learn from mistakes. And if we want machines to be perfect, then they wouldn't be able to learn. So that's a limitation that it's inherent in limits of formal systems, in the sense that not making mistakes is equivalent to being consistent, so that everything that is true will always be true, and everything that's false will always be false. And we want our machines to be reliable. Let's say we want 1 + 1 always to be 2. And then that limits their creativity. Of course, there's the debate like, well, at some level, they can be deterministic, and then at a more abstract level, they can be more flexible. So it's a bit like, okay, the hardware doesn't change, but the software can change a bit. Because in a way, also, we cannot change our physics, we cannot change our chemistry, but at some point we can change the rules of our game. But again, we tolerate ourselves making mistakes in most cases, and then that allows us to learn. And from limits of AI, let me just mention a couple of them. One has to do with meaning or symbol grounding, but then I would ask your opinion, since you have interacted with sophisticated LLMs. Do you think they understand natural language?
Oh, well,
Could you elaborate why?
I guess sometimes if you type a short sentence, they will misunderstood the meaning of some word. They will answer in a way that you do not want.
Yeah.
So I don't remember a specific example that I think it to me it happened a couple of times.
Yeah.
So in that sense, maybe I'm using free version of ChatGPT. I don't know if you get a paid version, it will get better or not. But
Yeah. I mean, I'll be the devil's advocate. So I was last week in Morocco, and many people didn't understand me. So I would ask like, oh, could I have an omelette without cheese? And they will give it to me with cheese several times. Or, oh, could I have a plate of watermelon? And they will bring a plate of all fruits except watermelon. So, I mean, we tolerate errors in humans, and especially if English is not native language of anyone in the conversation. So it's like, okay, why are we so hard on machines when we are so tolerant with with humans that?
But I guess if the sentence become longer, then it will understand better.
But then could we say the same about LLMs?
I mean, by the way, not only language, I think even if you do that math computation, free version of ChatGPT give you a lot of like mistakes. So
Yep.
you do need to know the stuff. You don't let the AI control.
Yeah. Yeah. So I mean, in 1980, John Searle posed his well-known Chinese room problem. So it has to do with symbol grounding. So there's this thought experiment where there's an English person in a room, and they get some instructions under the door with some Chinese characters, and they have a manual on how to manipulate those characters. So there's these instructions, and then they manipulate the Chinese characters and produce an output, and the output is correct, but the English person has no idea what happened. So Searle would say, like, well, machines are in a similar way producing right answers. They have no idea of what they did. So, for example, they can play chess, but they don't have understanding of what chess is, or they don't have a feeling of what it is to play chess. And they can beat humans like that. But then had the opportunity of being with him a conference in 2004. So I asked him, well, but actually we can apply the Chinese room problem to ourselves, in the sense that we don't know how we work. and somehow we produce the right answers most of the time, but let's say we don't know what love is, but we say we are in love. I mean, if we would be put to the test, like, okay, what do you mean by love? Okay. And he told like, well, yes, precisely, that's the point of his arguments. It's not that, oh, we do have understanding and machines don't. It's that it's very difficult to define what understanding is. And therefore, it's very difficult to say whether machines understand or not. And a few weeks ago at the Santa Fe Institute, there was a meeting about artificial general intelligence. And the main conclusion was that it's too vague of a term to be able to measure it or to be useful, because, I mean, if intelligence is already a problematic term, general intelligence, it's like, how do you measure? And actually, there are many problems of measuring intelligence also in humans. So there's these IQ tests, but then so actually one definition of intelligence is the ability of getting good grades in IQ tests. Because of course there are different types of intelligence. And anyway, these are also related to the limits of formal systems, because we use mathematics to build computers and computers to build AI. So again, we want our computers to be consistent, and then that limits their flexibility. And about meaning in cognitive science, people speak about embodiment, that, let's say, when there are sensory motor contingencies, then that's what gives the meaning to symbols. Let's say, following Wittgenstein, it would be to say that meaning is given by the use we give to symbols or words or strings or data. So therefore, in order for machines to have meaning, they need to be embodied in a body, they need to be embedded in a world, they need to be inactive, continuously interacting, and what was the fourth E? Embodied, embedded, inactive, and what? Anybody knows about 4E cognition? Extended, yeah. So there's this idea that mind is not only in the brain, information processing, but it extends to the environment, in the sense that in many cases, most of the information processing to make an intelligent decision, it's information processed by the environment. So for example, when many animals navigate, they exploit environmental cues for their orientation, for their navigation, and so on. Yeah, so those are for East. And there's the argument that since machines don't have that yet, then that limits their abilities. But then there are other problems that are more of a statistical nature. So probably you have seen these images where vision algorithms usually confuse dogs with food or other items. And are you able to distinguish which ones are the dogs and which? Yes, sometimes one can also get confused. And I guess nowadays you can ask AI to produce image that will look somewhere in between those, and then it will be even more confusing. But anyway, with Mario Franco, who's doing his PhD here, and a couple of colleagues who were visiting professors, we published this work. So how to hide this? Well, anyway, we published this paper where we showed that, imagine you have these data points, and then you have some noise, and then more noise, or might not be noise, it's simply that you have overlaps in your data sets, then that limits classifiability. So that's another limitation for AI. If the data set has strong overlaps, then there will be errors. And that doesn't have to do with how much data you have, which algorithm you use, how powerful is computer, how many layers your neural network has. So what do we do in those cases? It's like, okay, we know we will have errors. At least that's better than just assuming that we'll just get better and better. And in artificial life, we have also other limits, like, for example, open-ended evolution, which there are many different flavors of open-ended evolution. So, for example, one is simply that we have new types of things, new things. But then that's relatively easy because a random number generator will just produce new patterns. But then like a more sophisticated type of open-ended evolution is that we have new kinds of things. So for example, at some point there were no mammals and then there were mammals. So that's a new kind of thing. So how to achieve in artificial systems this type of open-endedness? It's an open question. Some people say that it has been solved. Some people say that it hasn't been solved. And again, it's related to the limits of formal systems because at the end, here we are dealing with novelty, and the same if we want an AI system to be creative, and if we want to predict that, it's an oxymoron because by definition, if you can predict something, it cannot be novel. So if you want your system to be novelty, then by definition, predictability has to be limited. I mean, of course, we saw that almost by consequence of complexity, predictability is limited. But assuming that you could design a system and its environment in a controlled way in order to be able to predict everything, then one wouldn't have novelty or creativity in that system. So again, if we assume that creativity is part of intelligence, part of evolution, if we want, let's say, AI, if we want open-ended evolution, then we need to let go of predictability because then we need novelty. Yeah, and another limitation is that in a way, open-ended evolution is related with strong emergence because basically when we have new types of things evolving, these things generate new constraints on the original things that we were evolving. And how this strong emergence or downward causation takes place, it's not only something that we cannot predict, but something that we cannot prestate because we can only observe it after it happens. So that's something that, let's say, not only we don't have the tools, but we don't have the proper language to describe it and how to accept it. And there are also limits on causality that it's one of the most useful or necessary concepts in science. Like, okay, something causes something else. And we have Bayesianism, we have Judah Pearl's books on causality and so on. But again, they have limitations. One of them is spurious correlations. There's this website where you can get hundreds or thousands of spurious correlations. And now with generative AI, it will write a paper explaining that and also generate an image illustrating that. But then, of course, it's just a coincidence. And again, we don't have the proper tools to describe dynamical causation. So if we just focus on state spaces, which are extremely useful to describe dynamical systems, usually if we have interactions, meaning complexity, it might be that the states space will grow. We have dynamics, like there was this from for non-stationary spaces or changing state spaces, that we have, let's say, functions that change in time, and the way they change might also change in time. If we have huge combinatorics, then we'll have immense state spaces that will never be possible to be explored in time. If we have overlaps, then we'll have undetermined state spaces, which limits classifiability and therefore AI. And if we have correlations, we'll have probabilistic state spaces. And remember that when we speak about state spaces, these are descriptions of phenomena or abstractions or models. They're not the phenomena themselves. I mean, there are no real state spaces. And also when we speak about, for example, different levels of abstraction, that's also descriptions of the same phenomena at different scales, but in reality, there's no distinction between, let's say, cells and bodies. Let's say in multicellular organisms, it's just the same system. I mean, we have different descriptions. Okay, we can focus at the cellular level, we can focus at the organism level, and then try to define causality between these two, or between individuals and a society. It's the same thing, just described at different levels. So therefore, when we try to describe causality, by necessity, it's partly subjective because it's an observer that defines these different levels of abstraction. It's not something purely objective, independent of observer. And just to mention a few of the limits that we saw, when we have non-stationarity, we can use adaptation. When we have non-reductionism, we can use self-organization. If we have non-compatibility, evolution seems to have worked to explore these huge state spaces. And for non-classifiability, we have no idea. So sometimes it's not so much solution, but more to find a coping mechanism. Like, okay, we have these limits. How do we cope with it, or how do we minimize the damage it might cause? And yeah, so adaptation, it's everywhere in biological systems, so it's natural to use biological inspiration to build adaptive systems, and cybernetics has been doing that, and also artificial life and for recognition, they take inspiration from biology in order to build adaptive systems. And about the limits of objectivity, I mentioned already that when we speak about causality, that is partly subjective, but that applies almost to everything. And when we discuss about models in science, we had a deeper discussion about this, so I will not repeat it, but there's usually this distinction between epistemology, or how we know or how we describe the world, and ontology, how the world is. So epistemology is subjective, ontology is objective, but then we cannot have one without the other, because just like when we speak about ontology, by using language, we're already simplifying and subjectivizing reality. In order to decide which of potentially infinite epistemologies is most useful, we need an ontology to be able to contrast that epistemology. So to quote Schrödinger, the world is given to me only once, not one existing and one perceived. Subject and object are only one. Barrier between them cannot be said to have broken down as a result of recent experience in the physical sciences, for this barrier does not exist. So yeah, so we already spoke about problems with modeling. We can have complete or incomplete models. And yeah, there's some things that we can speak about, but then there are other things that we cannot define. Because in theory, that's something that Gödel strongly believed in, that if a human can pose a problem, then a human can solve it. And in theory, yes. And in theory, we should be able to understand everything, because it's like, okay, if we can perceive it, it is there, so then we should be able to understand it. But in practice, we're limited, and actually what is that big difference? It's some open thing. So with our formal systems, we will not be able to overcome these limits. It's proven. But then it might be that these limits are actually a feature, not a bug, not a problem. Because if Hilbert's program were successful, if it turned out that mathematics were complete and consistent and decidable, that would mean that a universe where that holds would have no space for creativity and evolution. So we wouldn't be here. Because in order for evolution to work, it is necessary to have limited predictability so that you can have novelty. So maybe we should better embrace these limits. And of course, this has implications not only for artificial intelligence, for artificial life, for complexity, for cybernetics, but for science in general. Because also it also has philosophical and ethical implications, because if we cannot predetermine most of the things that we think that we can be sure of, I think that gives an added value of life, because also we might be a bit nihilistic in the sense that, oh, if we can predict the value of life, well, if we can predict everything, then we could also predict the value of life. And then what is the value of life if we can predict it? But then if this is not predetermined, it's not even just to speak about free will. It's just about potential. And the fact that things are not determined, I think, is more positive than if they were determined. It might be tempted, especially for engineers, to be able to predict everything, and it's like, okay, then we can ensure that this will not fail. But as anybody dealing with engineering, we know that things happen and things fail, and we just have to adapt to unforeseen situations. But then I think it's preferable to have those unforeseen situations than to be able to control everything and then to be limited in much stronger ways. So I would defend that it's better to accept limits in science rather than ignore them, and also their implications for engineering. Whether some of these limits will be overcome or we just need to accept them and deal with them are open questions, so there's much to explore. Okay, so for Thursday and Tuesday, we'll have final project presentations. I was trying to log into Brightspace unsuccessfully, so I don't know. I still have to give you feedback on your advances, but hopefully I'll be able to do that today. And then there's a temptation of everybody to present on Tuesday. Then that defies the the idea of having it in 2 days, because if everybody presents on Tuesday, then we might not have time. So who would like to present on Thursday? Good. Yeah. I don't know, maybe I'm too
Maybe you can create a kind of a survey somehow, and then people go out to present
yeah.
Thursday then.
Yeah, I'll see about that. Yeah, I'll count how many projects, because also maybe I'm imagining.
People can see their feedback first and then decide if they do anything.
Yeah, and also as a reminder, the presentations, of course, it assumes that you already have results, but since there are 2 more weeks from this Thursday, 2 more weeks to finish your papers, it's not like, okay, now we already finished everything and it has to be done by Thursday. It's just the presentation, and then with the feedback of the presentation, you might still tweak a bit the paper. But let's say it might be that you haven't written any of the paper and you'll rush in 2 weeks. So let's say it's not such a big difference if you present on Thursday or Tuesday, but anyway. Yeah, I guess I'll put yeah, I'll see how many projects we have and how many should go on each day, and then from there we'll see how many will go on each day. Okay, questions?
So, this topic, I think what you're asking about LLM's ability to understand what you're asking. So I just want to share some comments on that. I think as humans, we don't understand other organisms, like we don't understand our squirrel things, but we try to study their like behavior.